Hello and welcome back to another homework video. So today I'm going to start by deriving the three-dimensional heat diffusion equation for Cartesian coordinates with volumetric heat generation. So if we look here at the cube, that can be the volume, and let's make an axis here as well. This will be the x-axis, z, and then the y-axis. So this is dx, dy, and dz. And we're going to look at how heat flows through these two faces, or through the volume. So we know that the net heat flow is going to be equal to the energy stored plus the energy generated. So the energy stored is the energy that's within the box or within the volume. And so we can measure what the temperature is, like how the temperature is changing, but then we want to relate that to energy using the heat capacity. So we can write this equation where the energy stored, or the rate of change in the energy stored, is equal to the density times the heat capacity times the change in temperature over the change in time, and this is by the change in volume. And then the energy generation, or the rate of energy generation, is going to be equal to the heat flow rate and then times the volume as well. And then for this example, let's just say that it's at steady state, so the heat flow in is going to be equal to the heat flow out. Okay, so looking back at the volume, let me move this here. Okay, so let's say we're looking here and here. So this is going to be heat coming in, and then this is the heat at this face on the right side, plus this like change in distance, which is the dx. And we can relate this, I'll rewrite it. Here it is. We can approximate this to be the heat flow times, this is going to be the change in heat over the change in position times dx. Or rather, we want to add these two. Add it. Okay. And then we can relate this back to this here, where the net heat flow is the heat flowing in, which is Qx, minus the heat coming out, which was the right side term. And then we can plug in what we just approximated over here and say it's minus the heat flow plus the change in heat over the change in position. And then we just get that the net heat flow is equal to the change in heat flow on the x-axis times the change in position, or over the change in position rather, with respect to dx. and this should be a negative. Oops. So now we can write this as an energy balance. That's going to be that the rate of energy stored is going to be equal to the net heat flow plus the energy generated, or the rate of energy generated. So now we can plug in the information from before, where the energy stored is the density times the heat capacity times the change in temperature over the change in time. This is part of the change in volume, or rather just the volume. It's going to be equal to the net heat flow we just said was the negative change in the heat over the change in position with respect to dx plus the energy generated, which is the rate of heat flow times the volume. And then looking here, we can apply Fourier's law. Which, if we remember it was that the heat flow is equal to the thermal conductivity times the area times the change in temperature over the change in position. And then this area here, if we look, this is all volume, this is volume, and then right here is just dx. So this area is really dy dz, and we can plug this in. So let's rewrite this. There's no change over here. This part is going to be d over dx times the thermal conductivity times the area, which was, we just said was dy dz, times the change in temperature over the change in position. And then the generation is still the same. So now we can factor out the volume terms here. And this part. Oops, I forgot. The dx is still here. There we go. Now we can factor out the volume. So we can just rewrite this. It's all going to stay the same except the volume term is not going to be there anymore. So it's still the density times the heat capacity times the change in temperature over the change in time. And then it's going to be the thermal conductivity times the change in temperature over the change in position, and then plus the rate of heat flow. And then we also have the thermal diffusivity, which is the thermal conductivity over density times heat capacity. So we can rewrite this again by dividing that over. It would be the change in temperature over the change in time is equal to, this is going to stay the same. This is now going to be alpha, or the thermal diffusivity, still times the change in temperature over the change in position, plus the heat flow over the heat capacity times density. And I'll simplify this as well while we're here. This is supposed to be the second derivative of the change in temperature over the change in position. Okay, so this is our heat diffusion equation, but if we look at it, this is just for dx. So this is just, if we go back from this face through this one. So we also want to do, or I guess relate this to these top faces, the top and bottom face, and this front and back face here. So it's the same equation, but we just want this second derivative term to be with respect to every face. So let's just rewrite this again. You're basically just repeating the derivation steps from before, but instead of having this in terms of x and dx, you're going to do it for dy and dz as well. So let's rewrite this one more time, where the change in temperature over the change in time is equal to the thermal diffusivity times the second derivative of the change in temperature over the change in position on the x-axis plus the second derivative of the change in temperature over the change in position for the y-axis, and then finally the second derivative of the change in temperature over the change in position for the z-axis. And then the last term stays the same, that it's still the rate of heat flow over the heat capacity times the density. And this is the overall heat diffusion equation for a volume using Cartesian coordinates. Okay, so now we're looking at a one-dimensional heat diffusion with heat generation where one side is insulated. So that's what I have drawn here. And then this is going to be at some length. And it's going to be, let's say x is equal to 0 over here. This is x is equal to whatever the length is. And we can use the heat diffusion equation from before. Copy that down. And then the total energy generation is going to be equal to what is leaving. So this energy generated, this is going to be times the volume. So it's going to be the cross-sectional area times the length. It is going to be equal to what's leaving, and that's going to be Fourier's law. So that's the negative thermal conductivity times the area times the change in temperature over the change in position. And then the areas here will cross out, and we're left with the energy generated times the length is equal to the negative thermal conductivity times the change in temperature over the change in position. So then we get that the change in temperature over the change in position is equal to the energy generated times the length over the thermal conductivity. And this can be evaluated at x is equal to 0 because that's going to be the left side. So then looking at the left side here, as x gets bigger, so as x gets bigger this way, the length increases. So that means that this length in the numerator is going to get bigger. So that means that the slope is increasing. If we look at this insulated side, it's insulated, so that means the slope is going to be 0. So this is going to be 0, and then starting from left to right, the slope will increase. Okay, so now let's look at a case of steady state two-dimensional heat diffusion with no heat generation. So let's say that this is the x direction and this is the y direction. And let's say on this side it's 100 degrees Celsius. This side can be 200. Down here, let's say it's 250. And then the top we can say is 310 degrees Celsius. And then we can use the three-dimensional heat diffusion equation from before. There, and then we're gonna do it for the two-dimensional scenario. So we're gonna use the same equation, but because it's only two-dimensional and we're focused on the x and the y axis, we don't need the z term. So this is the new heat diffusion equation for this 2D scenario. And then if we look back at the question, it's with no heat generation, so this term was equal to 0. So let's rewrite this again. Change in temperature over the change in time is equal to the thermal diffusivity times the second derivative of the change in temperature over the change in position for the x-axis plus the second derivative of the change in temperature over change in position on the y-axis. And then to apply finite differencing, this is the length of each of these blocks. Let's say this is delta x, and on the other axis is delta y. So for this, let's say that t is equal to some specific time times the change in time. And then where you are in the x direction is going to be equal to I times your change in position. And then we need the y direction also. So that y is going to be equal to j times the change in position along the y-axis. And that tells you like where you are within like this grid or in one of these nodes. So if we look back at the grid, if we are in this block here, this is going to be the temperature at position ij. So as the x and y direction are changing, that's what the temperature is at that block. So we can rewrite this equation using these terms. So the change in temperature is going to be the temperature ij. This is somewhere on this block, and this is going to be to the right of where we are because it's how temperature is changing. So it's the final minus the initial minus where the position that we're looking at on the block. It's going to be t to the n over the change in temperature. Oh, sorry, the change in time. And then this is going to still be equal, to the thermal diffusivity. That's going to be constant. But now we're trying to find the second derivative of the change in temperature over the change in position for the x direction. So if we look back here, we'll zoom in some. Staying along the x-axis, one block to the right is going to be the temperature at I plus 1. And then j is the same because it's still on the same y-axis. And then the one to the left is going to be t of I minus 1. And then j is constant again. And then if we're going to look at the y-axis, that would be the one below it is t, where the x is constant, so the I is still the same. This is J minus 1, and the one above it is Ti J plus 1. So we're going to use these terms for these second derivatives of the change in temperature over change in position. So in the x direction, this is going to look like the temperature this is going to be Ti plus 1 to the n minus T of ij to the n over the change in position on the x-axis. So then this part is between these two blocks, and then we need to subtract it from the change in temperature of these two blocks. This is minus the temperature of where we are minus the temperature at I minus 1 J, and these are both still to the n, over the change in position. And then this is a second derivative, so then this is all over the total change in position. So that's for the the x direction. And so we have to do the same thing for the y direction. So we're going to do this, we're doing the exact same thing. This is going to be the temperature at I j plus 1 to the n minus the temperature at I j over the change in position in the y direction, still to the n, minus the temperature at ij minus the temperature at I j minus 1 over the change in position. And then again, because the second derivative, the whole thing's divided by the change in position in the y direction. So we get this big equation here. Okay, so this is the final finite differencing equation, this here. But eventually we are going to put this into Excel to map out how this looks using these values of temperature. So let's simplify this further now so we can put it into Excel in a second. So let's say for this, when we simplify it, let's say that the change in position in the x direction is the same as the change in position in the y direction. So it's just the overall change in position is delta for the simplification. So now we can simplify this. So this part can come down because it stays the same. And then this section here, we can simplify this to be that the temperature at I plus 1 J plus the temperature at I minus 1 J plus the temperature at I J plus 1 plus the temperature of I J minus 1 plus 4 times the temperature at IJ is all going to be over the change in position squared. That's the simplified equation. And then if we assume that this is at steady state, this term cancels to 0. And then if we're looking at a long enough time, then we don't need these n terms here either. And so if we divide, if the left side is 0, and then we divide the thermal diffusivity over, and then multiply the change in position over, the final equation is going to be all these temperature terms equal to 0. So let's just copy that. And then, like I said, we don't need the ends anymore. So here's that. And then remember, we're trying to find what the temperature is here at the position ij. So this is going to be that T at ij is equal to the temperature at I plus 1, J plus the temperature at I minus 1, J plus the temperature at I J plus 1 plus the temperature at I J minus 1, all divided by 4. So now we can use this final simplified equation to model the temperature profile in Excel. Okay, so now we're here in Excel. So the values here we had, let's say T left, the temperature on the left, and that was 100 degrees Celsius. And then T right was 200 degrees Celsius. The temperature at the top was 310 degrees Celsius, and the temperature of the bottom was 250. And now we can select this, formulas, create, the left column is going to be the names, and the values are on the right. Great. Okay, so now let's model the grid that I had before. So this was T left. We can extend this a few rows. Okay. This is the top. Let's extend this one. This is T right. Okay. Okay. And then this is the temperature at the bottom. Okay, so this is modeling what the grid looked like before. Okay, so now let's use the equation that we had before, where the temperature at ij, so the temperature at this position, is going to be equal to the temperature of one to the right plus the temperature of the one to the left plus the temperature of the cell above it plus the temperature of the cell below it. And then this whole thing is going to be divided by 4. So this is what we get. And then we just extend this all the way down. And we can't do that. So it's because everything, these numbers are relying on the cells in all 4 directions, like around it. So, okay, we have to go back to files and we go to options, formulas. This is going to be enable here 1000, and now it allows us to do this, and we want to bring this over and there we go. So with this, it's showing what the temperature is at any position along the grid. So this would be, if I'm looking at this cell, this is just the average temperatures of the 4 cells that are around it. So this is how we can model the 2D heat diffusion within Excel.